Hey everyone, this is Paras Chopra, and I'm here with Dr. Anders. Dr. Anders is a senior research fellow at Future of Humanity Institute at Oxford University. So even though he holds a PhD in computational neuroscience, he calls himself an academic multitasker. And if you go to his website and his publications, you'll find everything right from philosophy to computer science, AI, future studies, and lots of interesting stuff that he's involved with. His academic collaborators include nanotechnology pioneer Eric Dexler and the philosopher Nick Bostrom. And if you hang around in the right circles, you would know Dr. Anders as the author of this very famous paper called Blueberry Earth, right? Where he took very seriously this question: what would happen if you replace Earth by an equal mass of blueberries? And maybe we'll get to dive that into that question as well in this. But welcome, Dr. Anders.
Thank you very much for having me here.
So your sort of bold conjecture, for lack of a better word, is that it may be possible that we are alone in this observable universe, and that's really bold. And when I was reading your paper, I was very intrigued, and I thought I must talk to Dr. Anders. But before we dive into why you think that's true, would love to learn more about your childhood and the trajectory of your career. What got you to actually ask this question, whether we are alone in this universe or not?
So I grew up in Stockholm in the 1970s in one of the suburbs. It was a very nice and boring place. So I read all the science fiction novels at the local branch library, all these fantastic things with aliens and space and new technology. And then at some point, I was maybe 7, I realized I want to make this real. How do I do that? I don't know how to design a spaceship. There's probably some science books about that. So then I started reading the science books and engineering books. And then I went to the municipal library and then the main library and then the university library. So then I ended up eventually in Oxford. So I always wanted to make the future real, both in the sense of building things that are futuristic. But I also realized that we need to understand things that might be important in the future. So we steer the course in the right direction. And that is why I ended up at the Future of Humanity Institute. So our mission is to think extremely big, extremely long term, and then ask the question, what should we be doing differently right now to ensure that we get to these very far off goals that might matter so much?
Right. So it's amazing that inspired by science fiction, you thought that the best way to create science, to realize that science fiction is to actually go out and study what future could look like and how do we as humans steer our destiny towards that direction, right? And
And one of the interesting problems is, of course, science fiction is not always a good guide to the future because stories have to be interesting, they have to be dramatic. Quite often it's more of a reflection of the present. But at the same time, it trains us into thinking, could things be very, very different? And I think that is an important skill because most people go through life thinking, this is what it is like. This is what it's always going to be like. And as soon as you start studying history, my director, Nick Bostrom, thinks I should read more history books than science fiction books. And he's got a point. You realize, whoa, the world has been very different. And that means it can be equally different in the future. The nice thing about history is that it proves that these things are possible. Science fiction, on the other hand, stretches our minds to imagine new things that has not been possible in the past.
right. So that's very very interesting. The contrast between history, because history has had happened, right? But when it comes to science fiction, there are almost infinitely many compatible with the current laws of science futures that could unfold. So how do you sort of constrain, say, your imagination, or in fact, how do you select between those infinite possibilities? What could actually unfold?
Yeah, so I think one needs to develop a set of tools to think about the future. To some extent, we're always doing that. When I go off in the morning to catch the bus, I'm making predictions that the door will lead to the stairway outside. I'm making a prediction that if I give money to the bus driver, he will accept my money and drive me to the center of town. Many of these things are predictions about the future, but they're so everyday that we don't realize that That's actually fairly similar to when we start thinking about bigger futures. It's just that we're less certain about those bigger and more long-term futures, so we have less well-developed tools. So when you do future studies, one of the easiest tricks is to look at the past, what curve the future. And this is surprisingly often a very good tool, because many of the guesses and predictions people make are surprisingly bad, yet we listen to the experts. And actually just extrapolating curves quite often works really well. The problem is when they don't work well. So when you get a change, and that happens sometimes, when the rate of change increases rapidly or decreases. For example, the amount of computations you could do per unit of money and second was essentially constant throughout most history, up until the 1940s, when it started growing exponentially because of electronic computers. We got Moore's law. And then people have been predicting the imminent end of Moore's law ever since. And the funny thing is, the classic idea about how computers improve stopped being true in 2006. Because at that point, the scaling of a microchip stopped happening as rapidly as it did because of various physical reasons. However, computations per second per dollar keep on growing exponentially because we're doing it in different ways in the future. Similarly, the amount of energy per person and the amount of economic growth per person was very tightly linked in the Western world from the Second World War up until 1970. It was a perfect line. Any economist would say, yeah, if you want to become rich, much more energy. And then that line, over a span of 1 or 2 years, broke and became a slightly weak horizontal line. People kept on getting richer, but they didn't use more energy per capita because the oil crisis meant that people started thinking about energy use. Now, if you can predict where a trend breaks, then you're really set. Now you can say something very important. Or you can say, actually, we might want to break this trend because if it continues, stuff goes badly. So these are simple tools. But then you have the tricky tools because you want to think about stuff that is not going on right. And at that point, I started leaning on the laws of physics and computer simulations. And I trust the laws of physics a bit more than my own software.
Okay. So what you're saying is that essentially it's a mechanism that is more important, because if you don't know the mechanism, for example, you would mistake the early part of an exponential curve as like a linear curve, or you may not be able to detect when, say, phase shift happened and so on. And that's the difficulty about like predicting future. And that's what I keep wondering. Essentially, if you're trying to predict, I know you've written papers on, say, different scenarios for humanity, but there's so many variables when it comes to even understanding the mechanisms behind where the entire humanity could lead. It just seems intractable. So do you make models of that? How do you... It seems intractable problem.
And I think it is in a very deep sense intractable to predict the long-term future of humanity, because in the micro scale, it's up to individuals to act. And you can't predict the behavior of individuals, even though I do think in some sense the universe is deterministic, give or take the quantum mechanics. That doesn't mean humans are predictable, because we're complex systems and we just behave in a complicated manner. And then you add a lot of humans together. The interesting thing is, of course, there are some behaviors that average together, even in large human groups, and become fairly predictable. On the other hand, there are other important things that don't average together. So the fate of humanity, to some extent, is dependent on our leaders not launching a nuclear war. That is very dependent on a few individuals and a lot of complicated diplomatic processes. And I think one can make a very good case that this cannot be predicted in any sensible way. We don't have enough data. It might not be a deterministic process. On the other hand, there are other trends that are very robust. I mentioned Moore's law. In every step along the way has involved a lot of innovation and new technology, but it averages out to exponential growth. If we look at the overall wealth of humanity over the past 2,000 years, it's also grown exponentially, with slight wiggles because of the Black Death and world wars. They're hardly possible to see on the curve. Why is that so robust? Well, most people want prosperity. They're going to do sensible things to get prosperity. We build better economics and technical systems, so we get more of that. Now, when you start to analyze the future, you might want to use scenarios. So you bundle together different possibilities and you ignore the details of what's inside each of the boxes. That way you can have fewer choices and you can analyze between them. The real problem now is, of course, you want your scenarios to cover most or all possibilities. That is also tricky. But I think that is a little bit more tractable. The best thing ever is when you find a law of physics that means we know we can't go beyond this point. The speed of light limit, for example, there are very good reasons to think Einstein was right about that. And that limits what can be done in the future in a lot of ways, like humans can't spread faster than the speed of light. So there is a sphere expanding with the speed of light with limits of where humans can be arbitrarily far in the future. That means that we can say things about how much matter and energy would humans at some point have. We don't know what we might want to do with it. Culture is really hard to predict because people are innovating all the time. People come up with entirely new ideas about what a good life is and what we must do. But we can still know how much matter and energy they play around with. And that allows us to put some bounds on what can be done. So a lot of my work consists on trying to find these kind of bounds and seeing where are the big boundaries. And then we can look at big scenarios inside and see, okay, what is happening in here? Can we assign some probabilities? Or even better, say, what do we need to do to get to that really lovely scenario that looks good? And what can we do to avoid that dreadful scenario? If we can find those intervention points, then we're set.
Right. So just to capture what you've just described, predicting future of humanity is an intractable problem, not like building a bridge. So the variables in that problem would fall on a continuum. At the one end, you have variables like whether a world leader launches a nuclear weapon tomorrow. That's just very hard to predict. But at the other extreme, you have physical laws like you can't breach the speed of light. And in between somewhere, there are some like maybe long-term trends like from capitalism, where companies would exploit whatever's necessary to maximize their profit, and maybe that what fuels Moore's law. And similarly, from predicting aggregate of humans, maybe you could take a few things from our evolutionary psychology or background that people would want to do X, Y, Z. So what comes out of this is a few scenarios. And obviously, because this is future of humanity, you put probabilities because these all are uncertainties associated with it. And your work is really to see how do we steer this to a more preferable outcome versus non-preferable outcome, right?
Exactly. And that is also why talking even about probability becomes slightly tricky. Normally, we like to talk about probabilities that don't change when you mention them. But if we do our job at our institute, tell people, look, there is a high probability of something really bad happening. We need to do something about it now. If people listen to us, that actual thing becomes less likely. So there is an interesting interplay here between predicting the future and shaping it. And this fits us rather well. We're located in the philosophy department, even though we're very interdisciplinary, because we need philosophers to deal with these really weird things that happen. Similarly, but even by observing certain probabilities, you might also affect them. So the most famous examples are, of course, in quantum mechanics, where literally observation has an effect on the system. But we also get strange biases that we humans, by being intelligent observers, must exist on a fairly peculiar place in the universe, because most places in the universe don't allow observers to exist, which means that when we look around at the world, we're not seeing the average world in the universe or the typical states of that. We're actually seeing something very peculiar and special. And that is something you need to take into account when thinking about risk and possibility.
Right. So you have a tough job because you're talking in probabilities and you're talking about future of humanity, and many people are just not able to deal with probabilities. I mean, if you tell someone there is X% chance that this bad scenario will happen, I'm curious what's been your experience trying to persuade people who are in a decision making capacity, but they just don't understand that probabilities are there for a reason, and these scenarios could actually be real, even though the probability could be quite less.
Yeah, I think it's a profound problem that many decision makers don't understand how to reason about probabilities. But there is a bigger field, and that is reasoning about uncertainty. And at this point, many executives and decision makers actually are much better. It's just that they don't think very much in terms of numbers. And that is a bit of a problem because when you're calculating with numbers, you can use things in a rigorous way. You can be fairly certain about that the results are at least internally consistent. When you're reasoning about possibility and uncertainty, things might become more inconsistent. Sometimes that's all right because we actually don't have a consistent view of the world. Indeed, many executives are brilliant at reasoning about uncertainty, but wouldn't recognize a probability even if it hit them on the head. So sometimes reformulating the problem into the language which is used work better. One very fruitful form, at least in some countries, is to talk about gambling. Would you bet on it?
Okay.
How much money would you actually put of your fortune on this? And that produces useful results because people think about money very differently from abstract numbers that researchers bring up. If they realize that, if I'm making a good bet here, I could make money, even they're just imagining making money, that forces them to adjust things much more. The problem is some people, by principle or religion, never. And some people are bad at it. But I think finding ways of reformulating uncertainty into everyday terms is quite good. One of my many hobbies is playing role-playing games. So there you play around with dice in various adventures. And if you play them enough, you start getting a feel for probability distributions. You roughly know intuitive the difference between one that is fairly narrow and sharp and one that is long-tailed and risky. So I think we need, when we educate the future of decision makers, to have them play more games.
Right. So let's say decision makers get what you're saying. Maybe they understand the probability. But how do you make them care for something which perhaps is so far in future? Maybe it's 1,000 years far out and 1,000,000 years far out. And I do know that Future of Humanity Institute works on several different time scales. You're not just going around and saying what's happening next year, but you're actually pursuing what could happen very long, far in future. So even if I understand the probability, again, you have a difficult job of making people care. So how do you deal with that?
I think this is a little bit like making people care for relief work in Africa or any other question. You need to use the right language for the right person. Generally, I find that there are some people who immediately get intellectual arguments very strongly, and they are, of course, easy to convince by just having a good logical argument. In other cases, you need to paint a very vivid scenario. This is where science fiction is actually quite important. The pictures we get from famous science fiction movies and stories are used by people when they think about risks and possibilities. This is not always good because many of these stories were made to be exciting rather than truthful or useful. So there have been, I think, a lot of damage done to the debate about how to make safe artificial intelligence by all the pictures of the Terminator robot. Because people think that the problem are killer robots running around. No, the problem is much more subtle. It's when you get an intelligent economy that tries to maximize the stock market value, regardless of what actual value it has, or something even more abstract. Yeah. But image is powerful. So, for example, when you start thinking about the long-term future, often people speak of future generations because we know the feelings we have for our children and the other young ones. And we can also, of course, think that they, when they grow up, are going to have exactly the same feelings for the next generation and so on. So that's one way of doing it. Another one is, of course, to observe that we shouldn't care less about people who are far away from us in space. And the same must be true for people who are far away from us in time. Space and time, after all, are the same. This works really well on physicists when you point out that this is exactly what Einstein pointed out. It doesn't work quite as well on normal people. On the other hand, you can speak about the value of the future and point out just how many lives there are. And you can do this abstractly or vividly trying to visualize just how many future people there are and point out that if we flub it right now, they don't get to exist. Or worse, they might exist in a horribly bad state. And These are not some of the tools you can use, but there are many more. Other people would say, yeah, actually, I don't care too much about it. And then you ask, yeah, but imagine the last copy of Mozart's music slowly rotting away in a room. But that music is lost forever. This is not an argument about people. I think most people would say that actually people matter much more than some sheets of the music. But that picture is quite powerful. So there are many different ways of making the argument. And indeed, philosophers favor various arguments and get into big arguments with each other about what truly matters. But that is kind of some of the tools I'm using. Yeah.
So talking about philosophers arguing, Dr. Anders, before we get into why we may be alone in the universe, I was curious, what is that you and other philosophers about future of humanity do agree upon? Because there would be disagreements on some of the things, but what is the general consensus of philosophers when it comes to future of humanity?
Well, if you take philosophers who care about the long-term future, first of all, they all tend to be long-termists. They think the long-term fate of humanity matters much more than a lot of the things going on right now. Obviously, things right now matter a lot. There are a lot of real people in pain. There are a lot of real problems we need to deal with. It's just that there are other things that matter tremendously much more. And that means that you need to figure out a balance, which is very non-trivial. And here you have some profound disagreements about how to do things properly. Now, the really interesting thing here is, what else do we agree on? And I would say, actually not that much. A lot of people around the office certainly have a lot of things in common, but if we even go over to a sister institute, Cambridge, the Center for the Study of Existential Risk, they have a slightly different angle. They focus on different risks. They get into other stuff. So there is an interesting problem here.
Okay, so what you're saying is everyone agrees when it comes to philosophers or future studies that future really matters, and probably it's underappreciated in terms of what we value. And what you're saying, not within the community, probably there's not a lot of consensus on what should we care about.
Well, I think in many ways there is a consensus about what we should care about. Existential risks are kind of top priority, because if we flub it right now, we lose all of the future. That's kind of central. Then we might discuss, okay, what else do we need to do right now? Are there certain values that need to be preserved, or certain things that need to be investigated? And people have different views. It's not like we're fundamentally disagreeing with each other, but the uncertainty is high, and you have a lot of people pursuing things in a very different way.
So what you're saying is that there is consensus around caring about existential risks, but because there is so much of uncertainty, if you have two philosophers in a room, they will end up discussing and arguing whether they agree on the specific amount of uncertainty, because there's just so many variables.
And it's also a good idea to have a lot of different minds working on the problem. So one of the main findings in the study of how good people are at predicting the future found by Philip Tetlock is that most people are fairly bad at it. But the interesting part here is that when you take several people with slightly different views, and not necessarily average together the views, but combine them, you can get more robust and reliable things. And this is true also when you do a lot of other systems in statistics. You want to have an ensemble of experts that are individually good at some domains, and you combine them in the right way, and you generally get better predictions and better estimation. So having philosophers argue with each other, if they're good philosophers, they listen to each other and develop views. Or sometimes they realize we can do an experiment to find out who's right here.
Right. It's sort of like having it sounds like a prediction market for philosophers. And I know Long Bets, the site, they try to do this very publicly. And it's interesting I think what I find interesting is that the debate within science, within research community is so healthy to bring out the best viewpoints. but I think externally all that debate could be viewed as, that experts themselves don't know, so why should we care? And that's a tricky part.
Oh yeah. So when you go to a climate conference, you're going to have people giving fierce arguments about why a certain way of modeling something is wrong. But that doesn't mean that we're thinking that, climate is not changing. It's just we think that your model is going to overestimate this type of change, while my model is doing much better. And then, of course, that debate, being forced to confront somebody who disagrees with in the right manner, is very productive. So when you hear philosophers argue with each other, that quite often gets somewhere. There are some debates in philosophy that have been going on for hundreds or even thousands of years, but we have learned a lot of things through those. But it's not like people are just yelling at each other forever. And the problem is, of course, it's hard from the outside to see what progress even looks like, because even the philosophers don't even know what progress looks like. So we quite often at FHI try to see, are there things that we can test that are actionable, where there is data, or whether one can actually do implementations and see, have it be scaled up and demonstrate.
Right. So, Dr. Anders, now I want to get to the main conjecture we've been talking about. So, in your paper on dissolving the Fermi paradox and the Fermi paradox, and also the recent paper on evolutionary transition, suggesting we may be alone in the observable universe. So, I'm very curious if you could unpack that. Why do you believe that we, when I say we, I mean intelligent life, we may be alone in the entire observable universe? I mean, it just seems both exciting and scary at the same time.
Yeah. So the Fermi paradox is not really Fermi's or a paradox, as a paper pointed out. But the story goes that Enrico Fermi and the other physicists at Los Alamos at the atomic bomb project had a lunch, and they started talking about extraterrestrial intelligence. And then Fermi asked, where are they? So I like to call it the Fermi question, because it seems like we have a very big universe with a lot of sites where life and intelligence could perhaps emerge, and a lot of time for it to do so. And then if you multiply that with some reasonable probability, you ought to see a lot of intelligence out there. We don't see that much. We have a fairly empty sky. So something must be wrong, and that is why people call it a paradox. There is some kind of tension here. Now, what we argued in the first paper was that people quite often do something wrong when they try to reason about the uncertainty going on here. So there is the famous Drake equation, which is kind of a shorthand way of reasoning about how many intelligent species are there. So you basically multiply the number of stars with a fraction that have a planet, fraction of those planets that could have life, the fraction of those planets that could get life, times the fraction that develop intelligent life, times the fraction of them that develop intelligent life that then radio signals become observable, and then you multiply that with how long they survive. And then you get an estimate of how many there should be out there about right now. Now, most people who bring this up admit that most of those later factors we have no good idea about. The astrophysics ones, how many stars there are and how many planets there are, we're actually getting decently good data about. So people typically put in some guesses of it, and they admit that they had data. And then they get the result, and they again say, yeah, this came out from my guesses, but this might be helpful. The problem is, when I guess a number, I should not just say one number. I should actually say something like, okay, here is a range where I think it's very likely to lie inside. It's not just one number. And the result of the Drake equation should not be one number, how many civilizations there are, but some probability distribution. It turns out that this makes a big difference, because when you put in reasonable numbers that fit with what we know in science, you get a very wide range of possibilities. So you actually can get, if you put in somewhat optimistic guesses, you can get an average, which should expect to be a lot of intelligent life in the galaxy. But there is also about one chance in 3 that we're alone in the observable universe. So you have a very skewed probabilities distribution. There is a long tail going towards very few intelligent civilizations. And this is just by looking at our state of knowledge.
Right. So if we look at the Drake equation, which is a very simple model to estimate what is the likelihood we'll see the intelligent life around us, you're saying there are several essentially factors which are multiplied together in, say, simple probabilities. And some of the factors we have a good idea about, say, rate of star formation, number of stars with planets, and so on. But some of the factors we don't have a good idea about because the only evidence we have for those factors is ourselves on Earth. So there is no way to estimate probability of an intelligent life per planet, and that means, I mean, you could just get any answer you want if you put in an optimistic number. So what you're suggesting is that you recommend and you've used a range of values, and if you put in those range of values, there's just 1 out of 3 chances that we may be alone in this entire universe.
Yeah. And now you might, of course, say, yeah, but I don't agree with your ranges of values. I want to put in my own, which I think is totally fine. It's just that if you want to avoid our conclusion, then you need to claim that we actually know the probability of life emerging on planets and probability of intelligence emerging on planets with a rather high precision, which we don't. Any scientist that claims that they know the exact number, they're doing some very bad science. So they have some very weird argument for that. Basically, the effect comes from that vast uncertainty we have about how likely life is. Because life showed up relatively early in the history of Earth. So that might be a hint that it's actually fairly easy. But it could also be that Earth was ridiculously lucky. There are very few planets in the universe with life. We happen to be just on one of them. And there might be other reasons, which I described in other paper, why life might show up early, despite being very hard. And even if life is easy, it could be that most life in the universe doesn't evolve there. It might develop a coding scheme that allows it to replicate, but not to evolve very fast. So most of it never gets beyond single-celled organisms for star planet orbits versus a red giant and engulf the planet. We were just lucky to have this genetic code that's pretty good at evolving. So in just a few billion years, it can produce observers thinking about genetics.
Right. So you're suggesting that the factor with most sort of uncertainty is, say, if you have a planet, what's the likelihood that planet will have an intelligent life? And the way you've modeled this in your second paper is you've essentially tried to sort of estimate, what has to happen for intelligent life to evolve. And you suggest there's several evolutionary transitions that have to happen. For example, abiogenesis, which is creating life from nothing, and then the prokaryotic to eukaryotic stage, and then you suggested sexual reproduction, and then multicellularity, and then finally, once all of these transitions have happened, then perhaps another transition to intelligent life. So now I'm very curious, how do you sort of, I think one of the things that struck me from your paper, which was very clever, was to use this argument that us having evidence of our own intelligent life on Earth is some sort of a selection effect. And to estimate, to do justice to the right estimations of this probability, you have to accommodate for the fact that we exist. So could you maybe just talk about this a little bit more? How does this factor into estimating probability of intelligent life?
Yeah, so observer selection effects really make it hard to use data from Earth, because it could be that life is super common. Every planet in the universe has that. Or it could be that it's super rare. Only a few planets in the entire universe has life. And similarly, observers, they will, of course, always be on a planet with life. So when I look out of the window and see living beings outside, I should not be surprised, even if life is super rare in the universe. Given that I'm an observer, I must exist on a planet that has life. Now, there might be other steps leading from the first life to observers. Probably you need to develop some form of nervous system, brains you observing. And you probably also need to develop a more complex metabolism because single-celled organisms don't make very good brains. So there is probably at least 2 steps. Exactly how many steps there are is debated. There is a lot of interesting discussion in biology about what were the really hard steps in evolution For example, multicellularity is one step I don't think is that hard. Bacteria who divide, if they are slightly sticky, they tend to stick together and form agglomerations. And that's the first form of very simple multicellular life. It actually seems like it evolved several times on Earth independently. So I personally don't think that's one of the really hard steps. But eukaryotic cells that contains various organelles like mitochondria and chloroplasts, they seem to have evolved just once. And when you look at the processes that need to go into for that to succeed, there is a lot of tricky and unlikely things. Right now, most people don't really know how that happened. So we can just start out by assuming that to get an observer, you must pass through a number of steps that are fairly hard. And then you can do a probability model. Okay, life can exist for a certain time span on a planet before the sun burns out. What is the probability of getting observers before that happens? And the interesting part is, of course, that even if the probability is super low, on those lucky planets that still get observers, they are, of course, going to look back and say, life emerged early on here. And indeed, it jumped through a lot of very hard steps. But one of the really cool things, and this is the linchpin of the paper, what we're really making it work, is that the harder the steps are, the more evenly distributed they tend to be. If it was super simple to develop multicellular life, it happens 10 minutes after you get life on a planet, then you should expect that to happen very soon after you get life on the planet. If it's super hard, on most planets it never happens. On a few rare planets it happens before the planet becomes uninhabitable. On those planets where observers also show up, they need to have a probability to have it. So now you can't have a too short time interval between multicellular life and the end of the planet. So basically, the more hard steps you have, the more evenly distributed they need to be. So we were looking essentially at how is the statistical distribution of the steps in theory. And then we compared that to Earth, and we could conclude that it actually does look a bit like there are several hard steps.
Okay. So what you're suggesting is if something is really simple or easy in evolution, that should happen in rapid succession, right? If say multicellularity is easy, it should happen say as soon as you have maybe eukaryotes, and you would expect that to happen more often. And I was reading in your paper, I think current consensus is multicellularity happen maybe 40 times independently, which means it's not that of a hard problem when it comes to evolution transitions. But at the same time, say something like prokaryote to eukaryotic transition, that took a billion years, right? And it's happened only once, as far as we know. So that is what you're suggesting, that because, and also intelligent life took 4 billion years. So you're saying all these, because they happen, all these happen sort of like infrequently, they are sort of an evidence that because we exist and there is observer selection effect, the actual occurrence, the rate of occurrence could be much longer than what we're observing on Earth.
Exactly. The history of Earth is not good evidence for life and observers being very common in the universe, but it does work as evidence for that we are fairly rare. Now, it's worth noticing that this is kind of armchair astrobiology. I literally am sitting in my library with a computer and a lot of books, comparing data from various paleontological work that is actually out there in the world and do calculation. If you send a space probe to Mars and you find fossils, that changes conclusions quite a lot, because now we're getting extra evidence that allows us to update. So the good things about this conjecture is that we can test it. I can be disproven, which makes me very happy.
Right. And I think one of the things about your paper that struck me was that humans have evolved right in the order of magnitude of say sun's lifespan. So if sun's lifespan is say 10 billion years, and you estimate that maybe and Earth's biosphere lifespan maybe 5 billion years, so it seems humans arriving after 4 billion years just seems a little too late to the party.
Yeah, it's not so late that we need to really worry and hurry up because the biosphere is ending right now. Although as a long-termist, I do think we should start making plans to expand the lifespan of the biosphere too. But it is kind of a good hint here. It's not like we showed up a few million years after the ocean formed. If life and intelligence was really easy, we should expect it very early. So this also leads to these interesting questions about where are we in the history of the universe? And it turns out that Earth is a fairly late forming planet. Most planets probably formed a few billion years before Earth, because there was this big burst of star formation as the Milky Way formed about 10 billion years ago. And we are kind of late to the party. And that is, again, a little bit hint that if intelligent life emerges and then takes over the galaxy, and no other intelligent life shows up because the whole galaxy has been turned into parking lots and shopping malls or whatever aliens do, then we would expect to be really early. Instead, we find ourselves that's kind of slightly late. On the other hand, in the history of the universe, the era with stars shining is going to last about 1 trillion years or more. And now we're suddenly very early. We're kind of at the early start of having stars with planets around them. So another interesting question, why do we find ourselves around a rather bright G2 star, rather than one of those little dim M dwarfs that are going to shine for billions and trillions of years?
Right. Yeah, and you make a prediction for that in your paper.
Yeah, so our prediction is that actually planets around these red dwarf stars are not going to be as habitable as we normally would like to think they are. Now, there are various good reasons why there might be problems having a planet close to these stars. They're rather dim, so you need to orbit rather close to have a habitable planet. So first of all, that's going to lead to tidal lock. It's always going to turn the same side to the sun. And for a long time, astrobiologists said, yeah, that totally rules out life. It's that freeze of the night side, etc. And then they got better climate models, and it turns out that actually you can have a pretty functioning planetary atmosphere and ocean of these worlds. A more serious problem seems to be, though, that these dwarf stars have very big flares. So besides the radiation, they might also erode away that. Now, up until writing this paper, I was still pretty optimistic about these planets. And then I realized that actually our argument gives a pretty good argument that there must be something wrong with it. Otherwise, we should almost surely be living a few 100 billion years in the future around a red dwarf star. We're not. That is a very strong hint that there is a good reason for life not to evolve there. It might also be that over the span of about 10 billion years, plate tectonics, radioactive decay inside the planet finds there is less volcanism, there is less movement of plates, and that stops the recycling of carbon dioxide, which also breaks the climate balance. So that might be another timing limit. It might be that we're living here towards the end of the era where planets actually can recycle the atmosphere.
Okay. So is red dwarf stars, I know they live 2 orders of more magnitude than sun, but are they also more in number?
Oh, yes. So there is this initial mass function that astronomers love to debate and analyze. Basically, how many stars do you get in different size classes? And basically, it's a power law distribution. You get a few very heavy and big stars and enormous numbers of very dim red dwarf stars. The funny thing is, of course, because luminosity increases non-linearly with mass, we see most of the really bright stars. If you go out and watch the sky, most of the stars you see are all unusually heavy ones that shine very bright. You will not see the red dwarf stars, but they outnumber greatly.
Okay, so your argument is that if life was possible around, intelligent life was possible around red dwarf stars, we should probably find ourselves around that because they both are more in number and they live a lot longer. But since we happen to find ourselves around a 10 billion lifespan star, it just seems the conditions around red dwarf stars might not be conducive to intelligent life to arise.
Exactly. And again, this is something we can test, of course, as we get better telescopes and start looking for Earth-like planets around other stars. I have no doubt that we are within a few decades able to tell whether there are life on other planets. And if it turns out there is a lot of life around the red dwarf stars, well, there goes the paper. But on the other hand, if we find that there are a lot of planets and maybe they used to be habitable, but their atmospheres got shorn off by the flares, that's kind of a good thing, at least for trusting that.
Right. And Dr. Anders, you also talk about Mars, that if we find commonalities between Earth and Mars when it comes to common origin of life, that's also a prediction of your theory?
Yeah. So there is this long-running debate about where did life originally start. And the standard assumption people make is, okay, somewhere in the oceans of Earth far back, something happened to create life. But there is a competing theory that said, yeah, well, actually it happened in an ocean of some alien planet very long ago. But meteor impacts splatter the mud and the rocks that contain bacterial spores around, and they might move between planets and maybe even solar systems. This is known as the panspermia. It's been controversial and debated for a long time. In recent years, people have become more and more convinced that actually, at least inside the solar system, it's not implausible that over a span of billions of years, rocks do move between planets. We found meteors on Earth that seem very much come from Mars, and presumably the opposite is the case. So suppose we go to Mars and we start finding fossils. At that point, the important question is this related to us, or did it start on its own? So if we find that there was a biosphere on Mars, but it has the same fundamental genetic codes as on Earth, then we have good reason to think that, okay, maybe life is fairly common because it spreads between planets by rocks. On the other hand, if life evolved independently on Mars, it's using some different genetic code, even if it's died out by now, we would know that, life is actually fairly easy here. We should expect way more life in the universe because it evolved independently on two planets in the same solar system. So this is very useful evidence. And again, our way of reasoning suggests that we can learn a fair bit about our own chances because deep down, of course, why is the Future of Humanity Institute caring about alien life? Well, the reason is the last term in the Drake equation. How long does intelligent technological species last? That's the one we really want to figure out the value of, or at least the probability. If it turns out that life and intelligence is really common, but we don't see anybody, that's kind of scary evidence that there is something we need to look out for. If it turns out that life and intelligence is really rare, okay, we're lonely, but we don't have any more threats than the ones we create for ourselves.
Okay. So, yeah, I mean, tell me more about this, how long this, I mean, I'm interested in what is that still being debated. Is that an open question right now? How long does intelligent life last? If not, what are the other sort of questions which you personally are trying to currently address and answer?
Yeah, so the problem of how long civilizations last is an interesting one because it's a fairly recent one. And it was actually first asked by the people working on extraterrestrial intelligence. Certainly there have been people predicting the end of the world or the end of humanity throughout history. And many people have been having discussions about how long civilizations last. But most of that was kind of qualitative discussions about the Roman Empire becoming decadent, and that's why it fell. And then you got the astrobiologists actually having to think about it because they want to motivate by to use expensive telescope time to look for alien civilizations. So they actually tried to estimate how long does civilizations last. And this happened during the Cold War. So many leading people like Carl Sagan were somewhat pessimistic. He was kind of reading the morning newspaper about the latest nuclear tests and realizing we might end rocket soon. So at the lower end, it might be that technological civilization killed themselves within a few decades of becoming advanced enough to split atom. On the other hand, Sagan noticed that maybe a few, maybe not all of them, maybe just 1% survive and get wise enough not to do it. And then he believed they could survive for millions of years. As the debate continued, people realized that if you can actually start spreading into space, at this point it becomes very hard to kill off entire species. if you live in independent space habitats, you're pretty robust, especially since they could move over solar systems. Indeed, it turns out that if you spread across the galaxy, even at lower than the light speed limit, within a few tens of millions of years, you will have settled the galaxy. That means that actually an empty galaxy is very strong evidence that there are few intelligent species around. So Frank J. Tipler and Hart wrote a paper saying aliens don't exist based on the argument. They make a very, very bold prediction of this. And I think that's right. Advanced civilizations could probably survive very well, because I think the definition of being advanced is you're not vulnerable to getting wiped out by random chance or your own stupidity. And they might be rare, but given that they then hang around a long time, they might have big effects. This is, of course, tricky because the Drake equation is a good starting point, but it actually assumes a steady state galaxy where civilizations arrive and the others disappear. If you have a civilization that never disappears, the Drake equation breaks. It doesn't work anymore. You can't actually use it. You need to update it in other ways. And it might be that maybe we're at the point where intelligence is really starting the universe, and then it's going to gradually build up more and more of it over the next trillion years. So I've been working a little bit on modeling what would the far future of the universe be if intelligence spreads. What can it do? How dramatic a shift can it do? And what would be useful for it? So, basically, the sky's the limit. The laws of physics allow intelligent life to do enormous rearrangement of matter, enormous scale. We can literally move galaxies. Maybe we don't want, maybe we shouldn't, but it's physically possible, which of course also gives us another hint that we can start looking for really dramatic things far away in the universe and try to see, are there any neighboring super civilizations? So far, nobody has seen anything.
Right. That's what I was wondering one day. Maybe I'm not sure if scientists do that or not, but if we look out there and look at the stars, currently we assume that they evolve via, say, laws of physics. But if there is intelligent life out there, you should perhaps expect something which is completely unexpected. Maybe, patterns which are just generally not expected if natural laws hold, because there is some intelligent force or entity sort of trying to mine it for its own benefit. But we don't observe that, right?
So far, we haven't seen anything that looks like it. There are weird things that have made people very confused. The observation of the first pulsar made people very confused because you normally don't see that kind of regular pattern of radio signals in nature. So at least they were joking for a while, but maybe it's aliens. More recently, there is a star that got the nickname in the media Tabby star that has a very weird pattern of things obscuring its disk. It doesn't look like its planets obscuring the disk, but it doesn't look like anything else we know. And of course, we're all debating, was that evidence for some kind of megastructure orbit? Freeman-Dyson, in a classic paper, suggested that, advanced civilizations probably want to use most of the solar power from the stars. So they will just build a shell or a swarm of solar collectors around it. So we should look for the waste heat from that kind of installation. And there have been several surveys looking for such Dyson sphere. So far, no luck. But on the other hand, you can also say, maybe we're early. Maybe we get to build the first Dyson sphere, and then the second, and then the third. So it's very important to realize that intelligent life has the ability to modify the universe profoundly. We humans, we're in some sense just animals, except that we're animals who can kind of figure out things and then put things in motion and organize things so various chemicals come together in one place and then launch into space. That's a very weird physical process when you think about it. Yet we are physical process that cause these super unlikely things to happen. We arrange silicon atoms into microchips that do computations way better than normal rocks. And the same process can happen on larger and larger scales, because we're also self-replicating like other life. If we find a good habitat, there's soon going to be more people, more technology, more life. And that can totally overshadow many of our normal physical processes. So when we look out there in the universe, we should be looking for things that are not in equilibrium and are very unlikely given normal physics. but might be much more likely when their mind's involved.
Right. What's the star name? What's that object name you said, which has baffled everyone? I think I missed that.
So the nickname is Abyss Star.
Abyss Star.
Yeah. The actual name is the KIC and then a long number. And it's kind of a bit of a misnomer because you also want to call it the discoverer. Unfortunately, I can't remember her last name. It begins with a B. It's harder to pronounce, and that's unfortunately why her name went out as we can.
Okay. So just wrapping up now, Dr. Anders, I wanted to ask, let's say we're just the only ones capable of even asking this question, whether we are the only ones. It puts a lot of responsibility to actually cosmic responsibility on us to not just limit our potential or even not to just extinguish this isolated fire in the universe. So what do you recommend, say, people like me and others and just normal humans to be able to at least use their life in at least, if not maybe making this happen, from preventing this from sort of, not getting off this light?
I think the key part is to take the future seriously, realize that, yes, we might have this enormous responsibility. And even though I'm an individual and I don't have much power, I'm still here at a very unique position at the start of things. We just came out of the caves, and there might be billions of years of future ahead for our species. We have a very privileged position because we might make things worse, of course, by failing here, but we can also start preparing for the future. We can help to make the tools, to make the tools, to make the tools. We can start working on building institutions that are a bit better than they were. We can work on reducing those risks that are foreseeable and work on uncovering those other risks that we don't know about yet, but we would be very happy to know about. And I also think it's useful to just get that sense of optimism that maybe we're alone, maybe we have a tremendous responsibility, but we're also really unique. If somebody were to describe the universe and we're the only intelligent species in the universe, they better actually mention that, because otherwise it would be a very incomplete description. In a universe full of alien civilizations, well, maybe humans are just one in a long list. Maybe we got a lot more companions, but we matter much less. And I think from an existential human perspective, it's kind of useful to know that, whoa, you are a really interesting being, and you have your own intrinsic value, and you might actually.
Right. Thank you. I mean, that's an amazing and inspiring note to end this conversation at. Dr. Anders, thanks so much again for taking time out. Really enjoyed this conversation, and looking forward to your next set of papers. I'm just very excited to read them as well.
Thank you. Yeah, I'm also very curious about where my papers are going to lead me. I never know that before I start.
Thank you, and have a great day, Dr. Anders. Bye-bye.
You too. Cheers.
Cheers.